Now that we've looked at momentum conservation in one dimension, I'd like to take just a brief excursion into taking a look at systems where the mass is changing. And the classic example of this is the Tsiolkovsky rocket equation. Tsiolkovsky was a Russian scientist who uh, did most of his work around the end of the 19th, beginning of the 20th centuries. And very early in the 20th century, he got to thinking about issues of rocket propulsion. So the idea goes something like this. We're just going to look at a rocket that is in free space. We could think about launching one off the surface of a planet, but it just adds additional complication without really any additional instructive value. So we're just going to take a look at it in free space. So we'll say that the mass of the rocket is m, and that it's moving to the right here at velocity v. Now, coming off the flamey end of the rocket here, what we're going to do is we're going to think for a small period of time, delta dt. So as a physicist, I am doing the thing where I think of differentials as really tiny deltas. You can make this rigorous by saying it's delta t and then going and taking the limit as delta t approaches zero and all that. But we'll just say that over some small amount of time, dt, a chunk of mass is going to get ejected off the back of the rocket. Now, in the frame of the rocket, so let me just at the moment here erase this just for a quick moment. So in the frame of in the frame of the rocket, where the rocket decides that it's momentarily stationary, when the total momentum of the system would be zero, it would be ejecting back a piece of mass dm at, in the rocket's frame, we'll call v exhaust. I'm just going to label that as v exhaust. Now, with that thought in mind, I'm going to transform over to our frame, because since the rocket is accelerating, it's not an inertial frame. So we just need to imagine that we're standing by the side here watching this fly by. So in our frame, what we'll be doing is we'll be saying, okay, the rocket, before it ejects off this matter, was moving at velocity v. So this is before. And then after, we will have a blob of exhaust going out the back. Now this, bear with me for just a moment here. It's going to seem a little weird, but I promise this makes sense. We're going to say that the mass of the rocket has gone up by m plus dm mathematically. But we're going to observe that dm is less than zero. Now this piece of, so afterwards we're going to say that this rocket is now moving forward at the original speed v plus some differential increase in its speed dv. So dv here will be positive. And as far as the exhaust goes, in our frame, we would have been saying that the exhaust, before it got shot out the back, was going forward at v, but now it has slowed down by what the rocket said the exhaust velocity is. So we're going to go ahead and say that this is now going, that the rocket exhaust is going forward at, so we'll say this is a piece of matter minus dm. Let me actually go ahead and make that minus dm just to be consistent there. And in our frame, we'd be saying the exhaust is going forward at v minus v exhaust. Now, what we're going to do is we're going to calculate the momentum of the system at time t. Well, that's just mv. Good. Now at t plus dt, when we've ejected off the piece of exhaust, like so, this is going to be, well, we said that the mass of the rocket is now m plus dm. Keep in mind that dm is really a negative thing because the mass of the rocket's going down. V plus dv. And then here we said that the mass of the exhaust is minus dm, and it's going forward at v minus v exhaust. So being good physicists here, what we'll do is we'll say when in doubt, expand it out. So we'll FOIL this. This is going to give me mv plus mdv, do the outer. Inner, dm times v, but I'll rewrite that as v times dm. And then finally, dm times dv. That's that one. I'll distribute here. So I'll have minus v dm. I'm just putting that right there. And plus v exhaust times dm, just multiplying those through. So putting that all together, the pieces with the VDM pieces cancel. And this piece here is the momentum at time t. So I can rewrite this as momentum at time t plus mdv. I'm sorry, dv dm here. And then with this term dv times dm, the idea is that these are both differentials. And so they're both vanishingly small. Dm is a vanishingly small thing, and so is this. And as dt approaches 0, this goes to 0 faster than dv does or dm does quadratically. So what this means is that since it's a double differential, we can drop that out. All right. So what we get is that, and then we're still left with a piece plus v exhaust dm. All right. So again, doing the idea of treating differentials as really tiny deltas, we can say that the differential change in the momentum is what we have after time at time t plus dt minus what we had before. So that's going to be what we had at time t plus mdv plus v exhaust dm minus pt, and we can cancel that bit out. Great. Now there's one more thing that we can do. So remember we said that we were treating the rocket as just being out in empty space. So if we're out in empty space, there's no external force. So we can say that the change in momentum is 0 by the impulse momentum theorem if there's no external force. Now, if we were launching our rocket on the surface of the Earth, we would have an external force due to gravity. It just makes the derivation more complicated, but doesn't really give us anything new. So that's why I'm just thinking about being out in the middle of empty space so that I can clean that up a little bit. So rearranging this around, this gives me mdv equals minus v exhaust dm. Remember, dm is a negative number, dv is a positive number. Negative times negative is positive, so we're good here. And so I can go ahead and divide well, apply a theorem that makes it look like I'm dividing through by a differential, but I can also just say, if I'm thinking of these as really tiny deltas and then eventually taking the limit as delta t approaches 0, I can then let this become m dv dt equals minus dm dt times v exhaust. Now, in physics, there's a special notation. Whenever we differentiate anything with respect to time, we usually write that with a dot. So I just thought I would mention that off to the side. So here we can say MA equals minus M dot V exhaust. Now I look at this is from Newton's second law. This fact that the mass is changing with respect to time, we can interpret as the thrust. What's giving us the thrust? And we can already see that the more rapidly I want the velocity to change, the big deal here is I want to burn my fuel very quickly. In fact, this leads to an old joke in the rocket world. What's the difference between a rocket and a bomb? About 2.5 minutes. If it explodes in 2.5 minutes, it was a rocket. If it explodes faster than that, it was a bomb. And the idea here is just that we want the rocket to be picking up speed as fast as possible. All right, well, that was a bit of an aside. Let's go back to here. So we'll take this and we'll follow it through, and we can obtain what our final velocity is going to be after we burn our fuel. So what I can do is I can say dv equals minus v exhaust times dm over m. Now, again, here I can integrate both sides. I can do a definite integral here. I'll be integrating this from v initial to v final. And this will be minus v exhaust, which we'll treat as a constant. That's not really right, but if we're in deep space running a vacuum optimized engine, that is, near the surface of the Earth, v exhaust will change as the pressure changes. Part of the reason why the design of the rocket motor is different on the first and second stage of a rocket. But we're considering ourselves out in the vacuum of deep space. That will allow me to treat this as a constant and pull it out of the integral. So as long as I integrate from the initial to the final mass, dm over m, I'm good to go. Now, if you haven't had integration yet, I'm just going to tell you how you do integrate something like this. What you do is you look it up in a table. Oops, I forgot my dv over here. So this is going to give me v final minus v initial. This is going to give me, after I look this up in the table and I do some manipulations, I'll have lost my minus sign here, and I will have a natural log of m initial over m final. So I can turn this into the change in velocity of the rocket if I want. And that is Tsiolkovsky's rocket equation. And so what we get out of this is that you want the final, to get the biggest bang for the buck here, you want as much of the mass of the rocket to be fuel as possible, and as little be payload and, more importantly, rocket as possible. Payload is just part of the cost of doing business. You want to get that satellite up into orbit, it's going to weigh so much, and there you go. However, if you can lighten it up, then what you can do, that means you can proportionately reduce how much fuel you'll carry. And if you reduce how much fuel you carry enough, this means you might be able to get it into a smaller launch vehicle, which will then reduce the mass even more. This is also why rockets tend to get designed, I mean, obviously with safety factors, but you tend to design them to be as light as you dare get away with for the required strength and stresses. So lots of uses of composite materials, exotic fabrication techniques, such as 3D printers that print metal, for instance, to make rocket motors that do the same job but require less material and so forth. And also for staging, because well, I've mentioned this before in passing, but when you are operating near the surface of the Earth, there's air around you. That changes V exhaust. As you get into space, there's no air around you, so you'll have a different V exhaust. So what you'll end up doing is actually changing the shape of the exhaust nozzle in particular for the vacuum optimized version of this in order to get V exhaust back up to a nice high number. But the staging has some added benefit. It reduces the numerator and the denominator both. So this gives you a bigger number here, allowing you to have a bigger change in velocity. So this is why you tend not to design single stage to orbit rockets. Even if the Earth were airless, you would there comes a point where it's actually beneficial to have a duplicate engine just to get rid of the extra launch vehicle, the fuel tank, the walls, everything like that, to go further. So that's why some rocket designs are more than 2 stages. Is just that it worked out to be more efficient to go ahead and eject out a second, to make 2 sets of vacuum optimized engines and eject one of them. Rocket engineering gets really, really weird that way. But what we can get out of this is we want as much of the mass of the fuel, from a change the velocity perspective, we want as much of the mass of the rocket to be fuel as possible and as little of it to be non-useful payload, which means the launch vehicle itself. And we want to eject the exhaust gases out the back end of the rocket absolutely as fast as you can without blowing the rocket up or melting the rocket motors down. Alrighty, so with that, we'll continue our explorations into momentum conservation. But I thought this would at least be a fun little detour about what happens when we actually have to say Fnet equals dp dt instead of ma. All right, we'll catch you over in the next video.